Kia ora. I'm Jamie Wark, Lead Communications Engineer here at Halter. We make collars for the dairy industry to enable farmers to more efficiently allocate their pasture and manage their herds remotely. It's a pretty sweet piece of tech. Click a button on an app and boom, all your cows are up at the milk shed ready for milking. It's a massive time saver, and with a bit of forethought you can even schedule it all to happen while you're still asleep. Perfect if you want a bit of extra time at 6 a.m. to cook breakfast. I was lucky to have been with Halter from the first prototypes right through to market launch and now mass production. And I'd like to share with you a bit of our story of how we got here and talk about some of the challenges we had with what was probably a naive approach to radio comms. It was really about getting the right solution in place for the stage of the business where we're at. Optimizing anything in engineering is always a balancing act. Normally it's features versus money versus time, but in the radio world, it's range versus capacity versus power. I'll talk about a couple of ways to increase the performance of your network, and it's up to you to decide if that will double your range, perhaps double your payloads, or increase your number of nodes you can handle. In our case, we had a pretty clear target for how many nodes we needed to support, and we had a pretty modest power budget, being battery powered. And all the gains were really to allow a faster response for the system. Everyone wants to push a button and have the lights turn on immediately, but doing it out in the real world with hundreds of devices can get pretty hard. It's also super important for us from an animal behavior point of view that we're ultra consistent. The cows are trained by conditioning, and so you've got to give them consistent inputs and control messages to tell them, or so they can learn where the boundaries are and what the collar wants them to do. If one cow starts walking free before the rest, the temptation is for the herd to follow. And the rest of the collars will tell the herd to stay back and will needlessly stress out the cows. This means we have a huge level of confidence that the network's both working, and if there are any significant issues, such as an outage, then the farmer might get stuck with his cows being unable to be milked. But you most likely aren't farmers, and almost certainly didn't wake up at 5 a.m. thinking of remote control cows. So let's go through a simple example. I'd highly recommend anyone trying to scale up a project to start as simple as possible and get some metrics in place so you know what's happening and it all falls to pieces. When we started, our goal was just to hold some cows in a square and make sure all the promises we'd made to our investors were really true. We spun up a PCB, grabbed some quick and dirty Class A LoRa demo code, and configured all the collars to randomly check in with a status uplink once a minute. Queue some downlinks for our own API, and you can pretty happily control 10 to 20 cows. However, trying to run a full farm of 500 cows by sending downlinks to every cow one at a time gets pretty difficult and pretty painful, and pretty quickly saturates the net channel gateway. When I tried this, we lost maybe 50% of our traffic. Not a great packet error rate, but with a couple of retries, things were kind of working, and at least we had a starting point. There are two main reasons we were losing so much traffic. Firstly, every time your gateway flips into TX mode to send a downlink, it has to disable its receiver to avoid saturating the RF front end. A standard LoRa gateway can listen on 8 channels at various different spreading factors and decode a ton of incoming messages in parallel. But as soon as you do a single downlink, it goes momentarily deaf, and we were trying to send 500 downlinks at the same time. Secondly, we're having a whole lot of uplink collisions. Our fleet of devices transmits whenever they wake up from sleep. So if another device nearby also wakes up at the same time, tries to use the same channel and the same spreading factor, then we get an on-air collision. And we've probably lost one, if not both of the packets. Intuitively, as we added more and more devices, the probability of collisions became so high that at some point the devices are constantly retrying their uplinks, creating even more traffic and more collisions, and the whole network spins out of control. This leads into the first golden rule. As it turns out, 20% airtime is a pretty widely accepted practical maximum for a low hostile network. A low HAR in the sense where the devices aren't orchestrated in any way, and they just wake up and transmit without checking the channel at all. That pretty clearly lined up with the testing we've done on farm as well. And so the key thing to do was to restrict the amount of traffic we were doing by slowing down the devices and only sending uplinks to a point where we'd use up the 20% airtime. The 20% airtime is really about making sure there's enough extra buffer for if you get a peak in device traffic or an external disturbance comes along, then there's enough extra bandwidth there that things won't grind to a halt. So the key learning there is to make sure that you've got this ability to scale your device, to change the uplink rates in your devices, and you can balance things and move things around. If your firmware is locked, then you definitely want to put a bit of extra effort in. In the meantime, though, someone had gone and quickly magicked up an app and some fresh hardware, and now with the press of the button, we can hold our cows in a moderately complex shape. But that pretty looking app really wanted to do more than just hold cows in a square. We needed the ability to send new commands, shift the cows to the milk shed, and do all sorts of other crazy things. And all of a sudden, the network was on fire again, and we needed to find some more capacity. So we started looking around, and I found a feature called Listen Before Talk. LBT works by doing a scan on the channel prior to transmission to check if it's free. And if not, then it tries another channel. It's really good at avoiding uplink collisions, and on a busy network, it can reduce collisions by 20-30%. The main problem, of course, is called the hidden node problem. Basically, you have two nodes on each side of a farm or a hill, with a gateway stuck in the middle. The first node is fine with it, with any other collars nearby. It can see anything in its own little group, but it can't talk over the top of the hill. And so the device on the other side is unaware of the fact that it's using the channel. The gateway, of course, is stuck in the middle, can see both messages at the same time, and the packet can get corrupt. Of course, this isn't really a big deal for us with dairy farming, as typically all the devices move together in fairly large groups. This means we are able to avoid collisions within the group, and was a pretty easy, quick win for scaling. Of course, with TTN v3 also coming out, we're now able to do multicast. There was absolutely no point to be sending 500 messages to a cow at once, especially because downlinks are so expensive on the network. Multicast gives all your cows on the same farm an additional set of LoRaWAN keys. When the farmer presses that button saying it's milking time, you send one message encoded with the shared set of keys, and everyone gets it. So it was a real game changer, because from here on out we were starting to line up with that asymmetric capacity of LoRaWAN. We could send a single downlink message on one channel, then have all the nodes just respond back on their normal randomized uplink times with a message to say, yeah, I got it. That really reduced our traffic from 500 uplinks and 500 large downlinks to one big downlink and 500 small responses. It's basically a 40% airtime saving, and because of the multicast traffic can happen before the collar sends the uplink, it halved the amount of time between the farmer pressing the button and the collars falling back into sync. The next big thing that came along for us was animal well-being and heat detection. These had always been on the roadmap, but having nailed strip and break fencing, we needed to be able to monitor and find cows that were going lame and flag them for a vet. It's super valuable for the farmers to also know when cows are coming on heat, so they can accurately do artificial insemination. It's a massive job for the farmer at a particularly busy time of the year, and it was something the collar was perfectly placed to do. But as you probably guessed it, my job just got a whole lot harder. We now are generating this vast amount of data from the collar and basically tripled our traffic in one feature release. At the time, at least at this time, we were perfectly positioned to start using that LoRaWAN uplink traffic. What we really needed to do was make sure that the gateways were always listening across as many channels as possible. By changing the band plan and separating the up and down traffic in the frequency domain, like the US 915, AU 915, and the China bands do, we should in theory be able to use both uplink traffic whilst transmitting. This does require a hardware change to the gateway to make sure it's actually able to connect the RF switch. And where possible, you really want to try and fit a cavity filter or something to try and separate the frequencies apart. But where your application has lots of confirmed downlink messages like us, it was absolutely perfect. And it's a complete no-brainer. But of course, we're still bound by downlink traffic in our gateways because still bound by downlink traffic on our gateways because the nodes are still sending confirmed uplink messages. So unless they're evenly spread out in time, we're still getting nodes doing retries. But if we rethink the problem and instead of the node sending a one-off, yes, I got that command, you always send the current state instead, then we no longer require the guarantee those one-off messages were delivered, and we can start to use unconfirmed uplinks across either up to 64 channels in multiple different spreading factors and really increase our network capacity another order of magnitude. Or perhaps we should double our range by changing spreading factors. So it really doesn't matter where you're at with your application. We can all use some performance improvements, even if not to increase capacity, but just to increase efficiency and free up bandwidth for someone else. We're all playing in the same public bands after all.